Welcome, ladies and gentlemen, to the webinar titled Soil Structure Interaction. This is prepared by CAE Solutions LLC, and the preparer is Engineer Anelis Hernandez, MSO Engineer, Structural Engineer, and the presenter, yours truly, Julio Banks, MSME, CGC, Mechanical Engineer. Any questions, you could always contact us via email, contact@caesolutionscompany.com. This webinar is Soil Structure Interaction, SSI, and by simply defining the structure, foundation, and soil underlying the interaction through any type of loading distribution will demonstrate the power of CivilFEM for the realistic modeling and analysis of civil structural problems. CivilFEM is an easy-to-use software, which is the pre- and post-processor for the engine mark. The advantages of using CivilFEM. The user can involve nonlinear soil structure interaction, geometric or material in the superstructure, as well as the foundation and soil. Some types of nonlinearity sources would be material yielding in the superstructure itself, its elements. The yielding of the soil, second softening for instance. Base uplift or separation of foundation. This is a nonlinear effect. Yielding of foundation structure elements. The user can evaluate these nonlinear effects using response history analysis, which is performed in the time domain. The CivilFEM user can define different types of contact behavior between soil and structure. Application of direct method to perform SSI analysis. The consideration of secondary effects such as temperature, creep, and shrinkage. The construction can be analyzed for sequential staging to see the effect of excavations. Why is important in soil structure interaction? We will obtain more realistic load distributions. The load distributions in the structure depend on the soil properties, no matter whether the two structures are identical. More economic and realistic analysis results from the use of CivilFEM. The different options to simulate the soil in CivilFEM would be, number one, model the actual soil surrounding the structure. And we can model the soil supports using spring elements. Nonlinear soil models using CivilFEM, we have the Drucker-Prager plasticity model. CivilFEM includes options for elastic plastic behavior based upon a yield surface that exhibits hydrostatic stress dependence. Hydrostatic will mean stresses in all directions. Such behavior is observed in a wide class of soils and rock-like materials. These materials are generally classified as more coolant materials, which are generalized von Mises materials. The generalized more coolant model developed by Drucker and Prager is implemented in CivilFEM. Clay plasticity models. The version of the Clay model implemented in CivilFEM corresponds to the modified Clay formulated by Roscoe and Berlin. Again, the Clay formulation model by Roscoe and Berlin. 4 parameters constitute the formulation of this model type. One is the yielding conditions, constitutive laws, hardening laws, and flow rules. The More coolant plasticity model. CivilFEM includes a modified version of the more coolant. There are 4 constitutive formulations of this model. Again, similar yield conditions, constitutive laws, hardening laws, and flow rules. The different types of soils supported by CivilFEM are 1. Rock and 2. Soil types. Rock types will be sedimentary, igneous, metamorphic. The subtypes will be siliceous, clastic, and calcic. The rock class will be sandstone and flint. The soil types will be stock class gravel, which will be well graded, poorly silty, clay. The sand type will be well graded, poorly graded, silty graded, and clay. Silt low plasticity, silt high plasticity, clay low plasticity, and clay high plasticity. CivilFEM also allows the user to have other types, user defined, color generic, and the user has the option to define it based on known data from, say, building codes. The first application we'll see of SSI is a bridge soil structure interaction. The bridge description that we're going to analyze today. A wooden footbridge over a river has to be analyzed. That means we are given the geometry, and we will perform several types of analyses. The easiest one is static analysis, then soil displacement analysis, moving load analysis. We will demonstrate the differences and the importance of considering the soil in the analysis. Prior to so much potential, prior to so much power that exists today, these models will be analyzed separately. For example, the bridge will be analyzed first, and then the reactions will be applied to the supports. Now it's done simultaneously. The footbridge consists of a deck that rests on 2 lateral beams, transmitting its load to the parallel arches across several steel braces. The arches themselves are connected by truss members. Remember that truss members do not transmit bending because they act like pin joints. The arches are simply supported and have a hinge at the top of the arch. Now we move from the presentation to the actual exercise of the CivilFEM live. In the interest of time, we have the model already generated. In previous webinars, we have shown how these models are created. Now we're at a little bit more advanced stage. Now we have the modeled bridge and the foundation. Acting directly with the abutments, now we can see the foundation. That's the soil. And we remove that to make it visible of the actual reinforced concrete abutment. The loads are transferred directly to the soil via the abutment. And notice that different components are touching, therefore you have to create a contact model. We have 3 layers different in the soil. Which means that they may or may not have different types of properties, but the subdivision allows us to possibly perform data acquisition in the field. So not necessarily is because of the difference in soil as much as boundaries where we can evaluate what the response of the soil is for substantiation of the model. This particular soil is clay. This is conglomerate soil in the 2 layers. As we stated before, in the arches have the vertical member connected via hinges, which means that there's only rotation, and as we stated, because the members are truss member, there will not be any moments transmitted. And different colors represent the different types of materials utilized in this model. On the right, you see conglomerate is a rock. You see the type. Now we have clay. The bridge is made out of wood. The particular orthotropic material of the wood is shown on the left. Notice that it says generic. That means that the user has entered that data in CivilFEM. It is the responsibility of the user to ensure the quality of the data entered. We have also defined contacts between the different kinds of components, the abutment, the terrain. CivilFEM being the front end of MARC has different types of contacts. They can be invoked directly, and MARC being a powerful nonlinear analysis can handle these fronts quite easily. In this model, we have applied gravitational load, which is the law of self-weight. Also notice that the different components have different mesh densities, and CivilFEM can couple all these parts without the user having to match the boundary nodal distances. So we don't need to worry about that. In this model, we have 3 load cases: gravity, point load, and we have a non-uniform load. We can visualize the different types of loads by color. The soil has been modeled using solid tetrahedral elements. And the depths have been defined using shell. Notice that the abutment in blue on the left side of the screen is made with brick elements, hexahedra. We have cables. Using pre-stressed steel as the type. Now that we've seen the model and we have applied the loads, we proceed to load the results files. Based on the order of entry appearing or presented already, the first case that we want to display the results is for the gravity load case, which is self-weight or dead load. We will see the displacements in the z direction in inches, units of inches. CivilFEM is very versatile. While some FEA require that the Young's modulus be entered as KSI, you can enter the Young's modulus as BSI and you ask the results be given in KSI, for instance. Similarly, if you want different kinds of units, you could just ask for them and they come out instead of having to worry about the consistency of materials, loads, etc. Now, notice the displacement of the bridge and also the terrain, which means that if we have a deficient design, it would appear. The major displacement as expected is in the middle of the bridge deck. This was the displacement for the gravity load case. Now the next one is going to be the coupling of the dead load plus the point load in the center of the bridge. Now we see that the displacement is larger and it's about half an inch. Let's focus on two digits. Let's call it 0.45. These loads can be due to a vehicular load, a car that stops in the middle of the bridge. So it is not a moving load. And again, we will see moving loads further in this webinar. And finally, we'll show the distributed load, uniformly distributed load. We have noted the 3 different displacements for the 3 different cases. To compare them when there's no terrain, no soil. We are also able to visualize what occurs in the arch, the axial load in the arch. Now we're looking at the results list. We're looking for the axial. There are different results that can be visualized. As you can see, we are choosing the axial component, and we're going to ask for the units to be kips. It could be Newton, kilonewton, meganewton, or it could be US customary, in this case, kips. We can see the magnitude shown on the bridge, and the actual level is shown on the left. The maximum actual load is about 39 kips. We can also visualize the maximum principal stress. Now you can notice that the abutments is a concentration of stresses. And then we can see the reaction resulting from the bridge superstructure onto the abutments and the loads themselves. Finally, we can see the moment diagrams, bending moment in the arch. Now we can see the moments. The maximum will be about 252 kip inch, but also we could select any other type of unit such as kip foot. CivilFEM converts the results automatically and effortlessly. CivilFEM is a powerful software that implements the finite element analysis in a very transparent form. Now what we'll do is we'd like to see what would happen to the soil when we impose specified displacements. Again, this type of presentation shows you how things used to be done not more than possibly 10 years ago. Now we're going to apply this displacement actuator in the soil. It's the same model that we have been looking at. The only difference is that we have applied in the soil a displacement that is a function of time. Again, it's an imposed time history displacement that could be generated by a load cell. Now we'll see the response of the applied displacement history with each time increment. Now we're going to place here the displacements. Notice how CivilFEM displays the results regardless of the density of the mesh. We can rotate the model to see the variations of the response of the applied displacements. We can see the response of displacement in different orientations. Although in this case we have not introduced the level of water. It's possible, but today it will not be shown or demonstrated. Now we'll present the response of the bridge due to a moving load. The moving load was introduced as shown here. Now we'll see the results. And you notice that the response is moving in the horizontal direction. This will be vehicular loading. Now you see the different time steps. 1, 2, 3. See that the load is moving from left to right. This is a mid span. And we keep incrementing. The response is inverted. Interesting how powerful CivilFEM is and easy to model the desired response. I'll continue with the presentation. With the following example. The second application of SSI is a gravity dam soil structure interaction. We want to analyze a concrete gravity dam. The analysis that we are going to perform are static analysis, modal analysis, that means natural frequencies and mode shapes, and transient analysis. This is a gravity dam that holds water by means of the concrete weight that conforms the dam. The dam structure is made up of several separated monolithic elements, as shown in this figure. These elements are separated by vertical joints. The contact types selected between the different elements and between the dam and the ground is for the touching contact type. Touching contact type means that they can be active or deactivated touching or not touching. That's nonlinearity causing the matrix, stiffness matrix to change. In the statics analysis, the loading includes linearly increasing element surface pressures. As a result of hydrostatic loading, standard initial gravity loading is also applied, dead load. CivilFEM users can perform a transient dynamic time history analysis considering joint behavior. That means geometric nonlinearity and the material nonlinearity. You can define several excitation functions by using time-dependent accelerations, velocities, or displacements in different directions. In this case, a time-dependent x displacement history has been entered into the foundation as a BC, boundary condition, simulating ground motion induced by an earthquake. We will now see this model in CivilFEM. The tunnel is modeled as a 2D. After we do this model, we're going to see the third application as a tunnel into the, back to the second application. Now I'm going to open up the model and look at the gravity model. Now we can see the dam itself, which is soil. Then we see the model on the dam, cavity, a groove. Now we model using solid tetrahedra elements. Each one of these segments is making contact, the touching type. We can visualize the structure better if we could have the soil disappear as such. Now we can see the geometry. Now we can place the soil. As we stated before, we have different contacts, touching type. In this model, we have imposed some displacements. It's 40 seconds. And this is the history of the displacement in 40 seconds. We can also visualize. Notice the distribution. The x displacement in red shows the applied known history. We can proceed to display the results. We're going to load the file with the previously calculated results. and we like to see the displacement variation response. At each time increment. In the first time step increment, we see the following displacement, deformation, in inches units, US customary. Now we proceed to the next step. We will see a greater displacement in the lower portion of the model. We continue the time history of the Z displacement, X displacement, I apologize. Now we can see this enormous mass of concrete, how it deforms, and best visualized by removing the surrounding soil. We continue incrementing the X displacement that we have imposed. You can also notice how the soil has a perfect interaction with the structure. That is perfect compatibility. Now we're going to open the model analysis file. So we can see the different directions of model response. The natural frequencies, the reciprocal will be periods of vibration and corresponding mode shapes. I'm going to have the first mode, which is a fundamental mode. Now we can see a table here. The frequency in hertz and the reciprocal, which is the period in seconds. So you could think of hertz as 1 over s. We only extracted or requested the eigensolution to provide the first 10 modes. Now we're looking at the second mode of vibration. Now we're going to see the third mode. And we see we're going to continue increasing. It's important to note that what we're looking for is that we want any type of dynamic loading to be far from any other natural frequencies of the soil structure system. We have also performed our analysis, static analysis, where we have applied the hydrostatic pressure. Now we'll see the applied hydrostatic pressure on the dam in the lower portion of the model. Now we can see the response to such loading. As easily as we can see the displacement response, we can also see the loads. We can see where a concrete would crack, amongst other results. Again, CivilFEM is the pre and post processor for the solving engine called Mark. There is another version called ANSYS, but this one is using Mark. Now we can see the results, the effects of the imposed displacements in the X direction. Now we'll continue the presentation. The third application of SSI is a tunnel model in a 2D geometry. It corresponds to the metro station in Germany. The left portion of this view shows the terrain, the soil, and we see the structure, the stresses in the structure. On the right, has a sequence of excavation and construction. This is a staging model in CivilFEM. The first sequence is to show the excavation shown as A, then B, then we replace that excavated material with concrete. Then the excavation proceeds in alphabetical order. We have different phases, and they will be shown here. Again, in this example, we will analyze the following 12 stage construction excavation phases. We'll mention 1, 2, 3, and then 12. Phase 1 is excavation level A, excavation B, excavation C. Then you have the casting B, casting A, excavation D, casting D, casting C. Excavations E, F, and G for phases 9, 10, and 11. And last, phase 12, which is casting G. CivilFEM is able to calculate different stages and save them as different files. This model would include the elastic response of the solid structure with the soil, surrounding soil. Also, the response of the concrete with time is modeled. Shrinkage, and creep. Now, CivilFEM, we will show these shrinkage and creep. We'll now open the model. On the right, we see the materials and the color red and brown. Sand clay shown in time 0. This means this is the terrain in its original state, not including settlement. The activation time was 0. We also can see the clay, sand clay 1. In the activation time, we've shown a limit of 2 days. This represents a 2-day excavation period. Similarly, we continue on the different stages of excavation. We have a duration of 4 days, a duration of 6 days, and so on. In the concrete, you'll notice that we have an activation time of 8 days. This is the time expected for the concrete to be assigned and applied. We have defined several types of structural elements. As you can see in the mesh control. We have defined different types of load as phases. Each one of the phases have construction stages and contain calendar time of construction. Again, this is the time at which the load will be applied in a calendar time. We'll now see the results for different phases of construction. We start with phase 0. We're going to see the stresses in direction Y. We'll display the results by groups. Initial phase 0, which is the undisturbed soil. We see the phase where we remove the soil, phase 1, in zones A and B, as mentioned in the presentation. Similarly, we can visualize the stresses. For phase 1, notice that phase 1 we've already performed the excavation in zone A, as it was demonstrated in the presentation before. We call this gable left and gable right. Second phase is we do the excavation in the blue. Phase 3. Now extend the excavation from zone A to zone B. Observe the distribution of stresses of the terrain. The same process can be continued. We're going to look at phase 9. We see phase 9, how we remove the upper portion of the tunnel. The other areas have the concrete supporting the soil up and the roof of the tunnel. Now phase 11. In this view, we have completed the excavation of the tunnel cavity. Notice how easy to use CivilFEM is and the powerful features of viewing the progress of a construction in many stages. The last model is a fourth application on SSI. The homogeneous earth dam is modeled as a 2D construction process method. The homogeneous earth dam has the earth dams are constructed with natural materials. In general, earth dams can be designed to correctly fulfill its function using any type of available material. The model description and filling order is shown below. Loads are self-weight and hydraulic pressure, hydrostatic. Loads are placed on the upstream face during the last stage of construction. The material activation, that means the fields can be active or inactive. In CivilFEM, the cut and cover technique involves a non-linear stage process using material activation and deactivation. This is similar to gap elements that can be active or inactive when they're touching or not. Again, this is a material activation, which CivilFEM material properties are time-dependent. CivilFEM materials contain the activation time that controls the time at which the materials start acting. The material age equals the calendar time minus activation time. Those materials whose activation time is less than the calendar time will be active. Those elements whose material is inactive will not be taken into consideration in the formulation of the model, the stiffness matrices. By default, all materials activation time is set to 0 days, and all materials deactivation time is set to 36,500 days. So that will be 100 years. What we see here is the calendar time and stage process. Keep an eye on the surface of the model, 2 days, 28 days, 26 days, 84, 112, 140, 168, 196, and 224 days. Now we'll see this model in action in a live demonstration of CivilFEM. Now we see two types of materials, and notice the density of the mesh is always best to do it denser at the interface, as is the case here. The soil itself doesn't need to be that refined away from the surface, in keeping with the same Benan's principle of load application distance from boundaries. We have noticed that we have used plastic nonlinearity material properties for legal do confinement. Depict the cohesion found in manuals and the angle of repulse 20 degrees. We show the different layers corresponding to the time of the deposition. We also see on the right the types of analysis in calendar time. Notice at the ninth stage, we see the hydrostatic load and its magnitude. Notice that the loads are perpendicular to the surface, as fluids have no shearing capacity or negligible capacity. Now we're ready to see the results. for the first stage of construction. We see the results in the Y direction. The units will be set to inches. I will show the original deformation of the soil. Now at the seventh stage, and you can see the blue versus the red, which would be expected because it's a non-symmetric loading onto a symmetric geometry. The loading, remember, is on the left face of the dam and is applied perpendicular to the surface, being a hydrostatic load. Now at the last stage, called the ninth stage, we can see the plastic strain in the soil. Now see this. It's a plastic behavior, which is nonlinear response of the soil, and CivilFEM handles these kinds of phenomena quite easily. Notice the discontinuity because of the contact, which is expected. We are very appreciative of your attendance and your cooperation. We always welcome any comments how to improve the webinars. You will get 13 PDH value. CA Solutions is an approved provided by the Florida Board of Professional Engineering for continuing education. Our providing license number is 656. For more information, please visit our website. And please keep in mind that your success is our success, and if you help us model particular problems for your industry, we will take them into consideration based on the demand for such types of problems. Again, we thank you for your cooperation, and you can always contact us at this website. CivilFEM is available for special pricing to the attendees. And just contact us with your interest in further personal demonstration. We're willing to create presentations tailored to your company as individual or business entity.